a video that describes some electronics I assembled in order to measure the steering angle of a bicycle. You might reasonably ask why anyone would want to do that. I was motivated by what I felt was difficulty in steering a newly purchased recumbent bike, and building this measurement unit was a way for me to quantitatively evaluate that problem. So here it is. Here's the measurement unit right here that I built in order to measure the steering angle. So here's my LiPo battery that just velcros onto the front, and then I have a potentiometer which I have hot glued right onto the very top so that it's in the same axis of rotation as the front wheel. And from that I'm pulling off the wiper lead in order to give me the voltage. So I have 5 volts on one side of it, ground on the other, and then the wiper lead in the middle, and I'm measuring the voltage there. So that wiper lead goes into this Arduino Nano, which is then measured. I decided to go with a separate voltage regulator because I was having problems with the Nano and the SD card reader working with the 5 volts that it was producing. And then here is my SD card reader, which I'm saving all my data to. So what it does is it saves the steering angle. And you're probably asking why in the world would I want to measure the steering angle. But the thing that motivated me to put this on was the fact that when you're riding this thing, you're doing a lot of correction. It's really hard to keep it going in a straight line. So I decided that I wanted to get some kind of quantity of how much steering I was having to do in order to keep this thing straight. And so that's why I built this little thing. I recorded the voltage from the potentiometer wiper lead and then determined the steering angle from that. Then, because I would be periodically turning during the ride, I removed the steering angles below a reasonable threshold, which I determined to be plus and minus 8 degrees. Then I looked at the standard deviation as a way to quantify the steering activity that was required. Here's data for a short 2-minute ride where I'm trying to stay on a line in a parking lot and then turning at the end of the parking lot. Here's the data for another ride of 30 minutes where I'm looking at the standard deviation again. And again, I'm using only the data that is below 8 and above minus 8 degrees steering angle in order to calculate the standard deviation. And it turns out for all rides for this bicycle, the standard deviation of the steering angle turns out to be around 22.1 degrees. I also rigged a way to put the measurement unit on my Fuji touring bicycle. This is a bit of a mess of hot glue and sticks, but it aligns the axis of rotation of the potentiometer with the axis of rotation of the handlebars. Here are some results for this conventional frame bicycle. And it turned out that the standard deviation was always around 1.2 degrees. In conclusion, at least regarding the stability control, there's really no surprises here. Similar to an inverted pendulum, a bicycle is unstable because the CG is above the point where the wheels make contact with the ground. The shorter the vertical distance between the CG and the ground, the faster that time constant is going to be, which means that you'll have to respond more quickly to maintain balance. Additionally, the longer distance back from the front wheel to the CG means more movement of the front of the bike is going to be required to move the CG laterally. This means that bigger steering angles are going to be required. So the SlipStream, and in general most recumbents, have a poor CG location for stability and maneuvering. So it's no surprise that I find the SlipStream harder to maneuver than my conventional bike. For more useful information regarding the dynamics of bikes, the WikiLinks link is useful. On the right-hand side of this chart, you see the circuit and the components that I used for the measurement unit. All right, thanks for watching.